Thank you, Peter. My name is Muktar Bashir, and I'm from Aston University, working in the European Bioenergy Research Institute. And this research is a partnership with American University of Sharjah in the UAE with Yasser Makawi. Today I'm going to present modeling of steam air gasification of char in a circulating fluidized bed. So today I'm going to introduce the topic, show my project objectives, and how I model the reactor, and show you the results and conclude my presentation. Gasification is basically a thermal conversion of biomass or char or coal by oxidizing it with air, oxygen, or steam. The main products of this process is mostly char, tar, and non-condensable gases. And these non-condensable gases are mostly CH4, H2, CO, and CO2. The process is broken down into 3 stages. First, you put the biochar, and with heating it in a reactor, it dries up and moisture leaves the biochar. You get a dry biochar. From there, you do the pyrolysis or devolatilization process, which happens from 250 to 500. And this is the process that actually produces the initial gases. So initial gases, volatiles, and charcoal. So this charcoal is just a mixture of ash and char. And then in the main gasification process, which happens between 500 and 1,100 degrees, with air, water, or CO2, produces this reaction. So the charcoal basically is high in carbon content. So the carbon from that reacts with some of the gases and the fluidizing agents to actually produce more CO2, CH4, and this final gas is produced is the fuel gas. Fuel gas is mostly synthesis gas, so which is just a mixture of H2 and CO. The objective of this project is to pyrolyze biomass in a solar-induced reactor, and from there the products of the pyrolysis, which are the pyrolysis gases, and the biochar goes into a circulating fluidized bed reactor. And we modeled this using a software called Fluent to actually develop a model of the hydrodynamics and implement a tar cracking model in a circulating fluidized bed. So this is another model of the reactor, and is meant to show the meshing. I think it's to do with the light. So the products of the solar-induced pyrolysis process actually goes into a circulating fluidized bed. And this circulating fluidized bed is a bed that operates at a fast fluidizing regime. So heat and mass transfer is basically very fast, and you get a uniform temperature within the reactor, so it increases the rate of the reaction. Therefore, the gasification process can occur at a lower temperature. For the CFD model, I used the Eulerian-Uralium model, and this is basically just assuming both the gas and the solid operates in a control volume. So rather than other processes that you have to take the solids individually, for a Eulerian model, you just take bulk particles in a control volume. And for for the solid phase, in order to implement the solid phase model better, so I use kinetic theory of granular flow, which basically implements the drag law for the solid and other closure equations. And for the heat transfer, I use a correlation based on Gun to determine the Nusselt's number, and from there to get the heat transfer coefficient. Based on boundary conditions, I assume at the outlet, the outlet is at atmospheric pressure, and the process is fully developed. And for the gas phase, I assume no slip conditions, so the gas, there is less interaction between the wall and the gas. And for the solid phase, I use a shear wall condition based on a model by Johnson and Jackson. For the temperature, I just assumed an adiabatic temperature wall condition. So this is the approximate and ultimate analysis of the switchgrass char. Those are the rates of the reaction that I implemented using C programming language in the software. And for the gasification model, you have two reactions, the heterogeneous and the homogeneous reaction. So, for the heterogeneous reaction, also I did it in a C+ programming, so I programmed the kinetics in the software. While for the homogeneous reaction, the software can implement homogeneous reactions. So I basically just used kinetic values from literature to simulate the process. And these are the operating conditions I use, and these operating conditions are mostly based on run experiments and continuous optimization in the modeling software. For the concentration profiles, generally for a circulating fluidized bed, you have a dilute system because you need enough fluidizing agent to actually move the solids out of the reactor. And my results show that initially there's turbulence, where a lot of turbulence where the solid is going. There's a lot of turbulence at the solid inlet, and basically in a CFB, most of what happens is the gas pushes the solids up, and you have the solids falling by the sides. So you get like a conical deflection of the velocity profile. So for the solid and gas velocity profile, basically along the length of the reactor, you get a uniform flow as you go upwards towards the reactor, and you have most of the velocity being more at the core region. So like I said, you get a conical velocity distribution. For the temperature, so initially you have the gas temperature increasing very quickly, and this is to do with combustion reaction. And the issue we had here is just the char particles and the gas. There wasn't enough heat and mass transfer to actually increase the temperature of the solid significantly. Though it shows a behavior in circulating fluidized bed by which you get a uniform temperature distribution. We recorded the product composition, and the gas composition produced a heating value of 6.96 megajoules per Newton meter cube, which is quite similar for a range of a gasification process. And the tar content. So I implemented a tar cracking model. So I did two cases, one with the tar cracking and one without the tar cracking. There wasn't significant change in the tar content. It just reduced by 4%. But the issue is the model with the tar cracking simulates an actual experimental method. So when you compare the modeling and the experimental method, you get better results by implementing the tar cracking method. There was high carbon conversion efficiency of about 65%. And this is to do with the high combustion reactions happening. So burning all the carbon content to provide energy for the reaction. So this model is a switchgrass char gasification in the circulating fluidized bed, and I did a CFD analysis using Fluent and implemented tar cracking effect. The next step of my research is to solve the low temperature issue by using sand to improve the heat and mass transfer and carry out parametric and sensitivity analysis of the reactor using both experimental methods and CFD method. Thank you.